Next, the team decided to close the loop, feeding back the output into the input, and make the system stable. In order to do this, the team first had to start by determining what specifications the system wanted to have. The first specification that we decided on was that the steady state height should be less than 50 meters. This will give us a good height to clear houses, but is not so high that we have to worry about FAA flight plans or high winds at higher altitudes. Second, the team decided the rise time should be greater than 5 seconds. This was done so that the system was very slow responding. We did not need a twitchy system. We wanted it very smooth, such that the pizza was not damaged in the box from any rapid movement. This came out to find this requirement made that our omega n value needed to be less than 0.44 radians per second. Finally, our overshoot was meant to be less than 20%. This was done such that the overshoot and oscillations were minimized, creating a very smooth path for the drone and would not cause any damage to the pizzas. This ended up having a zeta value needing to be less than 0.2, while our phase margin needed to be greater than 45.6 degrees. We then took our transfer function, our open loop transfer function found in our previous parts, implemented our PI controller, and found that our transfer function was as stated there. We then implemented the mass of the drone dampening factors, our K values, as well as a BIBO stability to find our final transfer function here in the bottom left that has our numbers in it. That describes our whole system. Our system is shown as seen in the bottom right here, where we have a closed loop system with feedback coming in, a disturbance, and we have our controller for our PI system. This is a complete block diagram for our system and incorporates all aspects of the system. We then went to MATLAB SISO tool to verify our system. We have our plots as seen on our right here. We were able to get the phase margin of 46 degrees, a zeta value less than 0.2, our overshoot less than 20%, and our crossover frequency to be less than 0.44 radians per second. So it's all desirable and exactly what we wanted out of the system. We also liked the step response seen in the bottom right, as it had us overshoot, but it's a very smooth overshoot and very minimal oscillations, which is indicative of a very smooth ride for our system, which will mean the pizza arrives safely. We then went and analyzed how robust the system was. We decided to analyze the robustness of the system by changing the controller gain. On the left here, we have 10 times the controller gain in our system. As we can see, the phase margin decreases, the overshoot increases, the oscillations increase, and the rise time decreases. This is not desirable for our system, mostly down to the rise time being so quick. This means that the system is very twitchy and oscillates very quickly, which would most likely damage any pizza that we are carrying. For our 1/10 controller gain, we see a similar story where our phase margin decreases, oscillations increase, overshoot increases, but our rise time decreases dramatically. This decrease would mean that the system is very oscillatory, but would do so at such a slow rate that it would be okay. Overall, we found that the system was fairly robust, as it could handle a very large decrease in controller gain, and while wouldn't be perfect, would still function properly. But with a significant increase in controller gain, it would also be very unstable and undesirable. Here are our references, and that concludes our discussion on pizza drone delivery. Thank you.